Hey team, chemistry coach coming at you. We're going to look at some properties of matter. We're still in our journey on matter. And obviously we want to be able to go in the laboratory and analyze matter. So we've already talked about mass and volume, right? We looked at the difference between mass and weight. And we looked at volume as, the three-dimensional space something takes up when we define matter in one of our original videos. But let's look at a couple other things. Temperature. I want to take a little bit of time on temperature because we're going to spend a lot of time doing temperature measurements in lab and not just physically measuring them. We're going to be doing a lot of theoretical calculations using temperature as well when we get to gases and studying those. So to get a brief idea, I find a lot of students get heat and temperature confused, or they think they're the same thing. So I just want to briefly define these so you can understand that they're connected, but there's a difference between them. Temperature is just a measure of atomic or molecular motion. So say we've got a surface, right? So here's my calculator. So say this was iron or something. We can't see it, but if we could look on the atomic level, there'd be a bunch of atoms if this is, say, pure iron or something. And these iron atoms would be vibrating. So if I take a thermometer to measure the atomic molecular motion, boop, these atoms are vibrating. Say my fist is an iron atom vibrating, bonk, 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 bonk. That causes this to go up, right? So if this is vibrating faster, bonk, 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 bonk. Oh, that hurt. Don't hit the bottom of thermometers hard. Boom, 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 boom. So if it's vibrating faster, that's going to be higher. If it's vibrating slower, that's not going to be as high. So lower temperatures are slower or less motion. Higher temperatures are higher or more atomic or molecular motion. So that's a rough idea of what temperature is. That's related to heat because heat is energy transfer. And we're going to spend a whole journey just on heat. Heat is just a transfer of energy between two objects of different temperatures. If you ever, so a lot of people say I'm a hot person versus a cold person. I'm one of those ones I need to sleep by the window with all the covers off, just laying there going, oh, it's just hot all the time. And some people are like, oh, my hands are cold all the time. Blah, blah. So just make sure you get together with somebody who's opposite that. If you're a hot person, don't get together with a hot person because it's just sweat, right? So you find one where if somebody's a colder person and somebody's a warmer person and they snuggle together, the heat, because of the temperature differential, the energy as heat transfers from the person at the higher temperature to the person at the lower temperature, right? And then you come to the same temperature. It's so nice, so nice. That's a big oversimplification, but you've all felt that. Somebody takes their ice cold feet, sticks it on you, you're like, ah, right? But after a while, it's not too bad. All right, so just the difference between heat and temperature for you. We're going to look at three main temperature scales, Celsius and Fahrenheit, which are the two mostly used for measuring. So if you have a thermometer, in chemistry labs, they're always going to be in Celsius, right? So this would measure degrees Celsius here. Sometimes you'll see Celsius on one side and Fahrenheit on the other side. That's okay. But as chemists, we're not going to measure anything in Fahrenheit. We're going to measure things in Celsius. And a huge proportion of people in the world think in terms of Celsius. I know in Southern California, where I'm from, and I was raised on Fahrenheit. So when somebody says, how hot is it outside? People tend to be really lazy and leave the units off. I get on my kids all the time. They're like, yeah, it's 92 out. I'm like, what, 92 horses? 92 what? Right? Oh, they go 92 degrees Fahrenheit, Dad. Ha ha ha. And I'm like, if you were talking to somebody who grew up in Celsius and you said 92 and they assumed Celsius, they'd be like, we should all be dead. Right? So you've got to be super clear with your units. Otherwise, people can get very, very confused or shocked because you force them to make an assumption on what units you are intending. And some people may have been raised to think differently. Okay? So we want to be able to ultimately convert from Fahrenheit to Celsius because we're going to be measuring things in Celsius, but we might need to talk to people in terms of Fahrenheit or vice versa. And then Kelvin is another one, but we're not going to measure things in Kelvin. Kelvin is called the absolute temperature scale. We'll find out why in the next board here. But that's used more for calculations because you can't have a value below 0. These can be negative, and when you divide by a negative number, it gets really weird, right? You get these end up getting negative pressures and negative volumes. That just doesn't make sense. So we tend to do the majority of our calculations later on when we look at gas laws in Kelvin. There's another one I ran into, Rankine. I only saw it one time on some very obscure, I think it was a graduate record exam to go from undergrad to grad school. And it was like, what is this in Rankine? I'm like, I never even heard of Rankine, and I've never seen it since. But it was on a test to test how intelligent I was after I got my undergrad degree. I'm like, I never even read about it. I think it's used in engineering, but I don't really know. I've never seen anybody use it or talk about it. But Rankine, Rankine. Go look it up if you're bored. So let's take a look at these different scales, how they compare to each other, and then how we convert from one to the other. Let's take a look at our temperature scales here, side by side. And again, we're not going to do the Rankine one. Not going to go into too much of the history. If you're interested, you can dig into that. But Daniel Fahrenheit, early 1700s, roughly, put together the Fahrenheit scale, and we use degrees Fahrenheit, right? And what we're going to do is we're going to take and define. You could actually make your own temperature scale if you want to. All you got to do is define at what temperature on your scale. I could do like a degrees Celsius or whatever, and say, hey, by definition, water boils at this temperature on my scale. And water freezes, or melting point or freezing point. You could do either one, but most of us think in terms of out there, it gets cold enough where water freezes or hot enough where water boils. We tend to think that way. So if you define the temperature at those 2 points, then we can look and see reference to other scales how your scale functions, and we're going to end up deriving, knowing these values, what temperatures are defined as the boiling point of water. This is at sea level. And the freezing point of water. If we know those for 2 different scales, we can derive a mathematical equation to convert from one to the other, which we're going to do. We're going to do it. All right. I'm assuming you know these. If you grew up in the United States, you're probably more familiar with the Fahrenheit scale. If you grew up mostly anywhere else in the world, you're probably more familiar with the Celsius, or now they call it the centigrade. You may call it centigrade or Celsius. By Anders Celsius. And I'll tell you why they like the centigrade, but we tend to always, at least in that I've grown up, it's always been Celsius. And then the Kelvin scale. Now, one weird thing is Fahrenheit is degrees Fahrenheit. Celsius is degrees Celsius. So if you measure it, say the temperature is 22.5 degrees Celsius or 75.2 degrees Fahrenheit. But Kelvin doesn't have a degree on it. It's just, what's the temperature? 391.7 Kelvin. Not degrees Kelvin, just Kelvin. And you can thank William Thomson, a.k.a. Lord Kelvin, for that one. So I want to change my name to be Lord Locks. Yes, Lord Locks. Here we go. So from when I grew up, I always knew that water froze at 32 degrees Fahrenheit. That doesn't happen here in Southern California very much. And boils at 212 degrees Fahrenheit. And then on the Celsius scale, this is why scientists like this better. They say, well, let's say it freezes at 0 degrees Celsius and boils at 100. So you see there's 100, there'd be 100, if you broke this up into space, 100 equal spaces, that's called a degree Celsius. And that's where you get the centigrade, 100, get it? And then Kelvin, this would be 273.15 Kelvin and 373.15 Kelvin. And that is, my friends, going to allow us, we can now convert degrees Celsius to Kelvin, degrees Fahrenheit to degrees Celsius, back and forth any way we want. I'll provide you those equations on the exams, but I want to show you where they come from and what we're looking at. And two main things here. One, let's look at the difference between the values defined at the freezing point of water and the boiling point of water. Let's look at how many degrees Fahrenheit are in between those two reference points versus Celsius versus Kelvin. So let's do that pretty quick. We'll do that in black. So you could probably do this in your head, but just to double check, let's say 212 minus 32. Was that 180? Yep, thought so. Just want to make sure. So that is 180 degrees Fahrenheit between these two. So if I broke this up into individual units, there'd be 180 of them. Well, I can do 100 minus 0 in my head. So that's 100 degrees Celsius. So do you see a degree Celsius does not equal the size of a degree Fahrenheit? So if a degree Fahrenheit is this big, a degree Celsius might be that big. Right? So a degree Celsius is bigger than a degree Fahrenheit. And we can find that ratio. Let's look at Kelvin. 373.15 minus 273.15 is 100 Kelvin. All right. Well, that would mean a Kelvin is the same as a degree Celsius. That makes it easier when we're converting from one to the other. Very nice. So I'm going to do another board here, and I'm going to show you how to go from one unit to another. And we're going to account for two things. The size of a degree, right? Obviously Kelvin and Celsius are the same. Fahrenheit, Celsius are not. And we want to look at the reference point. So for example, if I'm going from degrees Celsius to degrees Fahrenheit, notice the 32 difference. So I'm going to have to add, so I'm going to have to adjust for the fact that the degree Fahrenheit is not the same size as a degree Celsius, and then add 32 to adjust for the fact that it's off at the reference point. We're going to use the freezing point of water. Same thing here, when we're going Celsius to Kelvin, I have to adjust for if they're different in size, and the fact that I have to go add 273.15 to get around the defined reference point, which is different. So let's start with Fahrenheit and Celsius. That's the most common one you're going to be doing when you're talking to people, at least if you're in the science community talking to people in the United States. And then we're going to be doing a lot of Celsius to Kelvin, lots and lots, when we get to gas laws later. So what I just talked about, let's kind of put numbers to it. If we're going to convert one scale to another, two factors we have to look for, right? The relative degree size, looking at the difference between the freezing point of water and the boiling point of water. Remember, that was 180 degrees Fahrenheit, 100 degrees Celsius, and 100 Kelvin. So if we look at those ratios, 180 degrees Fahrenheit between the freezing and boiling point of water must be the same as 100 degrees Celsius. Those are the same things. So if we take that ratio, 180 over 100, that's 9/5, which means 9 degrees Fahrenheit is the equivalent to 5 degrees Celsius. And this is by definition, we're going to use exact. If we look at the Kelvin to Celsius, we won't go Kelvin to Fahrenheit. We'll use Celsius as an intermediate. So we can go Celsius to Kelvin, Fahrenheit to Celsius, right? But we won't, and we could derive one to go directly from degrees Fahrenheit to Kelvin, but we're not going to do that. But you're welcome to, if you're bored. So if it's 100 to 100, that means it's a 1-to-1. So 1 Kelvin is exactly the same size as 1 degrees Fahrenheit. And again, a Fahrenheit is smaller than a Celsius. But there's our ratio. So when we derive these equations, we're going to be putting these ratios in there. And sometimes you'll see a 1.8 in there. 9 divided by 5 is a 1.8. I like the 9/5 because we're going to be canceling out the units. We also have to look at the defined reference point. We're going to use the freezing point of water. So by definition, that's 32 degrees Fahrenheit, 0 degrees Celsius, and 273.15 Kelvin. No degree on the Kelvin. Lord Kelvin, why? So we'll have to adjust for that. So if I, for example, want to take a temperature, I measure a temperature in degrees Celsius with my thermometer in lab, and I want to convert that to degrees Fahrenheit so I can talk to maybe my friends or relatives from America that maybe aren't chemistry majors and they don't tend to think in terms of Celsius, right? They go, well, could you do that to Fahrenheit, please? I'm going to have to convert degrees Celsius to degrees Fahrenheit by this 9/5 ratio, and then add 32 to get from Celsius to Fahrenheit. If I'm going from Fahrenheit to Celsius, I'll just subtract 32. If I want to go from Celsius to Kelvin, I adjust with the 1-to-1 ratio, which I can do in my head, and then I have to add 273.15 to get from Celsius to Kelvin. If I go Kelvin to Celsius, I'll have to subtract 273.15. Let's do it for degrees Celsius, degrees Fahrenheit, and show you how these two factors come into play. Let's walk through this one, see if you can do it with me. So let's say I measure something on my thermometer in degrees Celsius, and I want to convert that to degrees Fahrenheit. So the temperature in degrees Fahrenheit will be the temperature in degrees Celsius that you're provided or measured. And I want to convert degrees Celsius to degrees Fahrenheit. So remember, if I want to go degrees Celsius to degrees Fahrenheit, remember the 180 degrees Fahrenheit to 100 degrees Celsius or centigrade between the freezing point and boiling point of water, that was 9/5. Can you see what I'm saying? You see how the degrees Celsius will cancel out? It's kind of like a unit line equation almost. So what we'll do is we'll take that temperature we measured or were provided in degrees Celsius and convert that to degrees Fahrenheit using that 9/5 ratio. And again, you might see that as a 1.8 in introductory text. And then I have to adjust for, so that adjusts for the size difference between a degree Celsius and a degree Fahrenheit. And then I have to adjust for the difference of the numbers assigned or defined at the freezing point of water. So it's 0 for degrees Celsius and 32 to Fahrenheit. So if I'm going from Celsius to Fahrenheit, I will have to add 32 degrees Fahrenheit to that. Ho, ho, ho! There's your equation there. It's pretty easy to do. Now, if I want to flip it the other way and convert degrees Fahrenheit to Celsius, so let's convert degrees Fahrenheit to degrees Celsius. We don't really need to rederive anything. Let's just rearrange this equation and isolate this. Okay? So if I want the temperature in degrees Celsius, see if I can do this right off the top of my head. I want to isolate this. So I'm going to put 30, I'm going to subtract 32 from both sides, right? So if I want to get rid of that first. So I'm going to take the temperature in degrees Fahrenheit and subtract the 32 degrees Fahrenheit from both sides. So now that's gone, right? It's over here. Then I want to get rid of this. So I'm going to multiply both sides by the inverse of this, correct? Or you can see here, there are 5 degrees Celsius for every 9 degrees Fahrenheit. Oh, and you can see how the degrees Fahrenheit cancels out, leaving you with Celsius. So you just move the 32 to the other side by subtracting 32 on both sides, and then get rid of that by multiplying both sides by 5 degrees Celsius over 9 degrees Fahrenheit, and you've isolated the temperature in degrees Celsius. This is the one I will provide you on exams. I would expect you to be able to derive that one from it. All right. Let's do an example problem, and then what we'll do is we'll do the same thing to go from degrees Celsius to Kelvin. If you're on it, see if you can do it ahead of me. But let me throw up an example problem and how to track uncertainty through these, because you've got a multiplication where you're limited by fewest significant figures, and in addition, where you're limited by the largest absolute uncertainty, aka fewest number of decimal places. I find students get the uncertainty wrong all the time. Here's the type of problem you might see on a quiz or an exam. Definitely we'll do this a lot in lab, probably. So let's say we go in lab and we measure room temperature, or maybe the temperature of a beaker of water that's been sitting at, in the air for 5-10 minutes. So it's probably equilibrated to room temperature. And we stick our thermometer in there. Remember this, make sure this doesn't touch the bottom of the glass if you want to measure the water itself. If you're just measuring the air, don't grab that with your hand, because that's your hand temperature. Boom, that'll go screaming up. And so you just hold it out there. And let's say you get, after 15, 20 seconds, it settles to a 20.4 degrees Celsius. Labs are cut, kind of chilly. It's maybe usually a little warmer outside, but this is a typical temperature you'll see. I've seen lab temperatures range anywhere from 18 to 24. In California, it can get, 23, 24. That's a nice toasty kind of day when the air conditioner isn't working real well. I've seen it get below 18 degrees Celsius, very rare. That's when your fingers start going, yeah, I'm having a hard time, getting my calculator going. So 20.4 is a pretty comfortable temperature in nice, not cold, but a comfortable lab. Well, what is that in degrees Fahrenheit? Some of you look at that and that you're just like, oh yeah, that's great. It feels good to me. If you're a Southern California person raised like I was, you look at, actually I was raised in Minnesota, so that's actually pretty warm in Minnesota. I would look at that and go, what's that in Fahrenheit? Could you put that in Fahrenheit? You want to be able to communicate with everybody, so you want to be able to do these conversions. See if you can do that for me. Pause it and try it yourself and see if you get what I got. All right, you ready? So the temperature in Fahrenheit is the temperature in Celsius, and convert it, right, to Fahrenheit. Whoops. And add 32. That's something you don't have to memorize it. You can derive it, though. You don't have to memorize. If you can derive things, you don't have to memorize them. But I would provide you this on the test. So let's pop it in there. So what's the temperature given? 20.4 degrees Celsius. Let's convert. Pretty easy, right? I always like to provide the equation just in case somebody doesn't know where that comes from. Put everything in there with the units. We can see that degrees Celsius cancel out. So let's take 20.4 times 9 divided by 5. And these are exact. That 9 and that 5 are defined values, so those are exact. So we're going to be limited to 3 significant figures. So take 20.4 times 9 divided by 5. We have to do this in 2 steps. As a chemist, we need to do it in 2 steps because we have 2 different rules. We've got a multiplication rule limited by significant digits, and we've got an addition rule limited by largest absolute certainty or fewest decimal places. You can't do that all in 1 step. A mathematician would if they're not concerned about uncertainty, but a chemist is concerned about uncertainty. So we have to do it in 2 steps. You're like, no, no, no. So let's see what we get here. Let me switch back to purple. So this term, I get 36.72. Good to 3 significant digits. You see that? So that's good to 3 sig figs. Let's add the 32 degrees Fahrenheit there. Now we're doing an addition. This is exact, right? Those are defined. This is good to 1 decimal place. Or you can think of it as plus or minus 0.1 degrees Fahrenheit. Woo! My little board's in the way. So if you think in terms of decimal places, it's 1 decimal place. If you think in terms of largest absolute uncertainty, that's to the 10th place, or plus or minus 0.1. Since that's exact, I'm limited to the 10th place, or 1 decimal point. So take 36.720 plus 32, and you get 68.72. Good to 1 decimal place, and that's less than 5 in the non-significant. So that does not round up, stays at 68.7 degrees Fahrenheit. So that's a pretty nice, that's a, it's cool. It's not warm, but that's a cool lab temperature. So just remember 2 steps when you're going Celsius to Fahrenheit or Fahrenheit to Celsius. 2 different uncertainty rules requires 2 steps. Let's go Celsius to Kelvin and we'll be done. See if you can get this one on your own, right? If you just follow the rules. Let's say we want the Kelvin, right? So that we want the temperature in Kelvin. So let's take the temperature in degrees Celsius. So we got to adjust for a degree Celsius versus a Kelvin. I wish you would say a degree Kelvin. Now remember, they're the same. They're 1 to 1. So it's 1 degree Celsius to 1 Kelvin. Exactly what we did when we went degrees Celsius to degrees Fahrenheit. It was just 9/5. So that's kind of silly, right? 1 to 1. So most people just ignore that part. And then remember, the water freezing point is defined as 0 degrees Celsius and what was it, 273.15 Kelvin? So we need to add 273.15 Kelvin. A lot of people don't do this specifically, so what they do is they just ignore this whole part. They just ignore it completely. And they say that the temperature in Kelvin is just the temperature in degrees Celsius plus 273.15. And they get, it's kind of sloppy, so think of this as a shortcut. Because you're actually leaving out a step, the 1 to 1 ratio. So technically we should do it in 2 steps, but most people just take the temperature in degrees Celsius, because that's exact. You're going to be limited to the same sig figs you're starting with here. And then when you're adding, you're limited to decimal places. So really all you're doing is taking that temperature in degrees Celsius, adding 273.15, which is exact. And you're limited by decimal places. Okay? So this is what pretty much everybody does. This is what you should do, but this is what everybody else does. Now let's flip that. Let's say we want to go from Kelvin to degrees Celsius. Let's flip it backwards. We don't need to rederive it, just take it and flip it. So just move that to the other side. Pretty simple, right? So the temperature in degrees Celsius would just be the temperature in Kelvin minus 273.15. That's the shortcut version of it. Pretty simple to do. So let's do one example and we'll be done with temperature. Yay! Here's an easy but kind of fun problem. The coldest temperature. What is the possible coldest temperature you can get? That would mean, since temperature is motion, that would mean the coldest you could get would be theoretically lack of motion. No vibrations, no movement of atoms or molecules. Just, nothing. No, nothing. That's defined as absolute zero or 0 Kelvin. All right? So Kelvin cannot have negative values. This is why it's called the absolute temperature scale. You've probably heard that. So there's all the values are positive, and the coldest you can get is 0. Well, that would mean the degrees Celsius and degrees Fahrenheit scales could have negative values. And I grew up in Minnesota. You'd walk out some days, it'd be, negative, 3 degrees Fahrenheit, -5, negative, I think I hit a -30 or 40 degrees Fahrenheit with wind chill factor. You're like, yeah, I'm done. Go back and get some hot cocoa, man. So let's go ahead and calculate this. What is it in degrees Celsius? Well, that would be the temperature in Kelvin. And remember, Kelvin's the higher one. So we have to subtract 273.15. So that's the shortcut version, ignoring the 1 Kelvin to 1 degree Celsius conversion. So these are real simple, which is nice because you do them quite a bit. So let's plug in our Kelvin value, which is 0 minus 273.15 equals negative 273.15 degrees Celsius. Right? This is exact, so there's really no uncertainty of tracking that one. But that gives you a rough idea of the coldest it could possibly get. Now, if you want to really have some fun, convert that to Fahrenheit. I don't know what it is off the top of my head. It's like -400 something degrees Fahrenheit. That's cold! You get into the cryo-freezing stuff. There's some cool movies with cryo-freezing. What was that? Demolition Man, I think. Sylvester Stallone and stuff. There was some where they get or some people cryo-freeze their own body parts in the hope that in the future they can extract the DNA and maybe regrow your body. So freeze your brain. There's some crazy stuff out there, but who knows? Who knows? Temperature. Now in the next video, let's take a look at how that and density overlap.